Professor Bialis here. In this video we are going to be talking about section 3.4, which covers slope. Slope is the definitive topic when we talk about linear equations, okay, and graphing lines. Now the stuff that we've done before is not as efficient as utilizing slope, and many of you may have been thinking that while you were watching those videos. However, graphing with a table of values, finding intercepts, those are things that are really, really important in the grand scheme of graphing. So that's why we introduced those ideas in this chapter. Again, they were not the most efficient way of graphing. There was a lot of work involved to find 3 points. When we get into slope and we graph with a slope, we can get 10 points in a few seconds. Okay, but I want to be very clear that those other topics are still important. When we talk about graphing, something like this in like a college algebra or pre-calc class, and that's even not that technical and complex. But when we get into that, there's going to be 7 things that we need to find. One of which is find intercepts. One of which is create a table of values. So again, I don't want you to think, well, after slope, then those other things are garbage. They are necessary for the grand scheme of things. Okay, so I just want to be very clear on that. Now let's get into slope. Okay, so same as everything else, we need to start by defining slope and what it really is. Okay, so again, this is section 3.4, and we are talking about slope. Okay, there are a lot of ways you can describe slope. Okay, one of which is a rate of change. Okay, things change over time. How quickly are they changing? Okay, you could also think of it just generally as a measure of how steep a line is. Okay, is a line going to be like this? Well, that's not a very big slope. This is going to have a big slope, okay, because it's a very steep line versus something like this. Okay, another way you can think of it is a rise over a run. Okay, you can think of it as a change in y over change in x. Okay, if you get to the mathematical symbols in there, you want to say maybe delta y over delta x. That's just a symbolic way of saying change. Okay, all of those are good ways to describe a slope. Okay, it's not that we're going to be sticking with one of them. These are all kind of bringing across the idea of what slope is. Now, when we deal with slope, a lot of times we don't write out the word slope. We use that letter M. Okay, the reason we're using M, I believe it's a French word that means change. Okay, so that's where the M is coming from. Now, let's then talk about how we can calculate slope. There's a lot of different ways to do it depending on what situation you're in. First thing I want to look at is how we calculate a slope off of a graph. So let's say we have a line. I'm going to stick with this quadrant here. Let's say we've got these 2 points, and there's my line. Okay. A lot of times when I ask you to find the slope off of a graph, 2 points are going to be very visible for you. If they don't do that and they just give you a nice clean line, then make sure you're picking very nice distinct points, not something like this where you have to approximate. Okay, not that it's impossible, but then you are approximating and the answer might be a little off. So when we're doing this, remember that a slope is a rise and a run. That's what we're going to be utilizing most of the time with a graph, a rise and a run. So what we're going to do is basically follow the grid lines to go from one point to another. So I'm going to start here, and I am going to rise 2 units, and I'm going to run 3 units. Okay, so all I have is a slope that is a rise of 2 and a run of 3. 2/3, nothing more than that. If you get a fraction that is reducible, reduce it. So if I went up 4 units and then 6 units, I would reduce that down to a 2/3. Okay? Also, the direction that you do this doesn't really matter. Let's say I go from here to here, because the first time I went from the left point to the right point. If I go from this one to the left, then I would probably go down, which is a -2, because I'm going down, and then I would go to the right, which is a to the left, which is a -3. Okay, now that's okay, because remember, 2 negatives make a positive. It would be a rise of -2 and a run of -3. -2 over -3 is positive 2/3. Okay, so you do have some freedom with this. You still have to be, going from one point to another. Don't, go down here and then over here. You want to go from one point to the other, but you do have a little bit of freedom in the order that you do that. Okay, how about something like this? Let's say we go like so. Okay, so again, rise and run. Let's say I start from the left, go to the right. I am going to rise, actually fall, down 1, 2, 3, 4, 5, 6 units. Now since I was going down, I go -6. And then I run to the right 3 units. And again, that was to the right, so that was a positive value. So my slope in that case is a rise over run. Now remember, don't leave that. I should have a -2 over 1, or simply -2. This is one of those cases, if you do want to leave it as a -2 over 1, that's okay, because when we get into graphing using slope, it's really important that we still establish that there is a rise and a run. It's very easy to miss that run if you just leave it as a -2. Okay, but so this is the nicest, but this is totally acceptable as long as it's reduced. Okay. Now the other thing is, when we reduce that fraction, what we could be doing is reducing the step size in our slope. So instead of down 6/3, we could be going down 2/1, and look at what that looks like. Down 2/1. Down 2/1, down 2/1. Smaller steps, but you have the same overall result. Okay? So again, the reducing algebraically, reducing graphically kind of go hand in hand. Okay? So that is how we find the slope given a graph. Okay? Now let's say we don't have a graph. Okay? So what would that look like? Let's say I give you 2 points. So again, find the slope. And I give you 3, 1, -2, 4. So I want you to find the slope of a line that goes through those 2 points. Now, could you plot those points and then count the slope? You can. Okay. However, what if you don't have a nice graph grid? What if these points get really big? What if there's fractions involved? There's another way to do this, okay? So that brings us to our slope formula. Our slope formula is something you probably remember from the past. That is your y2 minus y1 over x2 minus x1, okay? Now, our y1 and y2, that subscript of 1 and 2 simply mean the first point and the second point. So what this really is your x from the first point, your y from the first point. X from the second, y from the second. And we're just plugging in. Okay? So what we get is your y from the second is 4, minus your y from the first, which is 1. Your x from the second, which is -2, minus your x from the first, which is 3. And then we just calculate from there. So what we get is a positive 3 over negative 5, and there you have it. I usually say throw that negative on top just so you don't lose it, but again, if you leave it on the bottom, nothing wrong with that. And there's your answer. Okay. One thing that I want to say, since we have these negatives here, if you look back at those examples that I had graphed up here, our first graph had what kind of slope? It had a positive slope, right? And that positive slope had a line going something like that. The second one was a negative slope, and that had something like this. Okay, whenever we get to graphing with slope, which will be in a couple minutes, okay, something I want you to be aware of is if you have a slope that is bigger than 0, aka positive, you should be expecting an upward trend to your line when you're going left to right. If you have a slope that is negative, you should expect a downward trend to your line. Okay? So what we're doing right now is just kind of tying all these things together. We got a slope off of a graph, got a slope off of 2 points. But as we get into the actual graphing portion of this, we want to be able to pull together all those little details that we hit along the way. Okay? Let's look at another example of this. Let's say we have negative 2, 1, and 3, 5. Okay, again, let's find the slope of the line that goes through those 2 points. Okay? So whenever you have a formula, if you're using it, you write it down. That way you're going to remember it. It's going to get stuck in your head. A lot easier than just trying to, look at it off the book. So slope, or m, equals y2 minus y1 over x2 minus x1. Say it again and again and again. Don't just write it down mindlessly. Say it as you're doing it. Okay, so again, let's plug and chug. We've got second y is 5. Minus the first y is 1. Second x is 3. Now be careful. Minus is automatically there from the formula, but then I plug a negative 2 on top of that. So there are 2 negatives there. 2 negatives make a positive. And I get 4 over 5. And there we go. Now, think about it. If I were to graph the line through those 2 points, what should it look like? My slope is positive 4/5, so it should be going upward like so. Okay? Always be thinking about that. Even if they don't ask you to graph, just think, if I were to graph, what would that look like? The other thing I'm going to warn you about is when we were plotting points in previous sections, it was always x comma y, but when we deal with slope, notice the y's are coming first. So please be careful with that. I see a lot of students, when they get into slope, they then plot points in the wrong order. So always be aware that points are x comma y, slope is y, then x. Okay? So that is what slope is, how to find it off of a graph, how to find it given 2 points. Okay? Now, what about if they give you the equation of a line? Okay, so how can we find the slope off of something like that? Let's say I give you y equals 1/2 x plus 5. Okay? Now, what we're going to need to have in order to interpret this is the understanding of what's called SlopeIntercept Form. Okay? SlopeIntercept Form is a way of writing a linear equation. Okay, the ax plus by equals c that we were introduced a few sections ago, That is called standard form. Okay, that's one way of writing a linear equation. Another way is the good old y equals mx plus b. Okay, notice we have a y term, we have an x term. But what's unique about this is that the y is isolated on one side. Okay, now why do we call it slope-intercept form? The slope and the intercept are clearly stated within this equation. Okay, as you can see, your m, just like we were defining slope with, is staring you in the face right in front of the x. Okay, now where does the intercept come from? Your intercept is going to be this b value right here. Now be careful, it is specifically the y-intercept, not the x-intercept. Only the y-intercept is clearly stated here. Now why is it the y-intercept? Because remember, for every y-intercept, the x has to be 0. If x is 0, the y value is simply the b at the end. Okay? So in this case, we would be able to say the slope is 1/2 and the y-intercept is 5. We would usually think of that as 0, 5. Okay, but still it gives you the value for that intercept. Okay, so slope is 1/2, y-intercept is 0, 5. So again, if they ask you what's the slope, done. You don't have to do any calculation for that. It's staring you in the face in the equation. Okay? Now, one added thing that I want to throw into this section that the textbook actually puts into section 5 is graphing with slope-intercept form. Okay? I want to explain how you can get a graph using this equation. We are given a slope of 1/2. We're given a y-intercept of 0, 5 from that b value. Okay? The way I like to say it is begin with b. You always begin with the b because that's a clear point. You can just plot that point. And I would go 0, 5. Okay? Now remember, slope, how are we calculating slope at the beginning? We were going from one point to another and counting that rise and run. Well, now we don't have the other point, but we have the rise and run to get to the other point. So from this y-intercept, what can I do? I can rise 1, run 2. Boom, I got 2 points. And here's the beautiful thing. You can keep making those steps indefinitely. Instead of rise 1, run 2, rise 1, run 2. And I can just keep stepping as many times as will fit. Look at how many points I had in a few seconds. If I was using a table, I'd still be writing my table out. Okay? Now here's the other good thing about this. If slope is 1/2, isn't that equivalent to -1/-2? Instead of up and right, what I could do is also go down and left. And look at how I am still on the same path. Okay? The more points you make, the more accurate your line is. Okay, so that's why it's so nice to be able to use this slope-intercept form when we're graphing. Very little work to do. We just need to know how to interpret. Okay, and this is why when we were doing the section 2, when we were graphing with a table of values, I said when you solve for y, make sure that you are putting the x first and you are dividing them individually. Because if you look back on your work from section 2, a lot of your equations should look something like this. It's just now we know how to read that equation. Okay? Let's look at a couple more examples. Let's say we have y equals -2/3 x minus 4. Let's say we have that. If they just ask you for the slope, you got y by itself. Slope is -2/3. Okay? If we want to go further and actually graph this thing, I'm going to use that slope. But I'm also going to use the fact that the y-intercept is 0, -4. Okay? Now, how do I graph with that? Begin with the b. Begin with the y-intercept. I go 4 units down. Now I have a slope of -2/3. Now, what should I expect here? I should expect a line going downhill because it's a negative slope. Okay? Now, we have negative 2/3. Notice the negative is directly on the 2. And the 3 on the bottom, as it stands alone, is positive. So I go down 2 and right 3. And I get that nice downward slope. What I see people do is they think negative 2/3 is a negative 2 and a negative 3. But two negatives make a positive. So make sure that when you plot your points, step back and you're going in the right direction. That's why it's important to know positive goes this way, negative goes this way. Because if you make a very easy to make mistake, you can catch it right away. And I can keep going. Down 2, right 3. Down 2, right 3. Down 2, right 3. I could go the other way. Instead of down and right, I can go up and left. And I'm on the same trajectory. Okay, connect those dots. And there's your line. Okay? How about this? Let's say we have that. Now, when we were finding slope, we always took the number in front of x. Okay? However, that only works when the y is by itself, when it's in that slope-intercept form. So the first thing we need to do here is get it in slope-intercept form. Okay? Get the y by itself, just like we did back when we were graphing with a table of values. So I'm going to subtract 2x. Remember what I was saying before. Put the x first, just so it's laid out in a nice common slope-intercept form at the end. Then I'm going to divide by negative 5. And now I'm in slope-intercept form. It's at this point that I can say my slope is 2/5 and my y-intercept is 0, negative 1/5. Okay? You tell me whatever they're asking for. If they just want slope, you have to do this, but then you just write that and you're done. Okay? But let's say they do want you to graph. Again, they're going to ask you to be graphing in section 5. Okay? How would I use this to graph? I start with this right here. I start with that y-intercept, which is negative 1/5. Now, again, I don't need to be exactly negative 1/5, but I need to be reasonable. It's just below that x-axis. Now, I have a slope of 2/5. I should expect my line to be going upward from left to right. Now, how do I move with the 2/5? 2/5, yes, that's a fraction, but we're interpreting them as two separate integer values. Rise of 2, run of 5. Do not think, oh, I got fractions here, I'm going to be adding fractions and all. No, you're not. Watch how I do this. I'm slightly below the line. I have my grid lines, but I also have lanes in between those grid lines. Same thing here, I have lanes. Try to fall within the same lane. Watch me. I'm starting here. I rise 1, 2 lanes, and I run 1, 2, 3, 4, 5. And I'm still slightly below that line. Again, I go up 1, 2 lanes, and then 1, 2, 3, 4, 5. Notice I'm in the same basic position in each of those spots. I can go the other way. Instead of up and right, I can go down 1, 2 lanes, and then 1, 2, 3, 4, 5 to the left. And I still have that same trajectory. I step back, I see that I'm going uphill, I'm on the right track. I connect those dots. And there we go. Okay? Again, if we were in section 2, we would do all this, and then we would have to plug in a bunch of values to find 3 points. Here, we just did some rise and run, and boom, 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 we got our answers. Okay? So, again, we know what slope is, we know how to find it from a graph, given 2 points, and now we know how to find it from an equation. Okay? There's 2 other examples of the equation that I want to talk about, and then one last idea involving parallel and perpendicular. Okay, we'll explain what that is in a second. So let's look at an example like this. Again, this is nothing new. You should look at that and say, I know what that is. I know that that is a vertical line. Okay, if I wanted to graph that, for instance, I go on the x-axis to 3 and I draw my vertical line. Done. Okay. How about slope though? We're talking slope in this section, so what kind of slope do we have on something like this? If I look at this graph and I just pick 2 random points on the graph, I'm going to pick this one and this one. How would I calculate that slope? Slope is always rise over run. So to go from this one, I go a rise of 1, 2, 3, 4, and there is no run. So what would that look like for a slope? If I rose 4 and I had a 0 run. Don't leave it like that because that's not simplified. If it's any value over 0, what we have is something that is undefined. Okay, that is an undefined slope. What about this? What if it was y equals -2? Again, we should look at that and say, I know what that is. That's a horizontal line. I go on the y-axis to -2, and I draw my horizontal line. Not a big deal. But we're talking slope. What kind of slope does that have? I'm going to pick 2 random points. Here. To go from one to the other. Do we rise at all? No. But we run too. So what does that look like? Rise, 0, run, 2. 0 over something that's not 0 is 0. Any vertical line has a slope that is undefined. Any horizontal line has a slope that is 0. Okay? So again, vertical line, undefined slope. Horizontal line, slope is 0. You may have heard in the past no slope. No slope is the same as saying undefined. I don't like using that because a lot of people confuse no slope to saying, oh, there's nothing, so there's 0. No slope would be the equivalent of undefined. So just be careful if you're going to use that. I tend to avoid it and just use these 2 right here. Okay? So, just a quick recap. If your slope is positive, uphill. Slope negative, downhill. Slope of 0, horizontal. Slope that's undefined, vertical. If you're mixing up the undefined and 0, think of a roof on a house. Can I have a flat roof? Yeah, it may not be the best thing, but I can have that. That has a measure of 0. It's not steep at all. But if it's vertical, can I have a roof like this? That's just a board sticking out of your house. So that's just undefined. That doesn't exist. If you're skiing, can I ski on this? Yeah, I can cross-country ski on this. Okay, it's not steep, so I say it's 0. Can I ski on this? That's what you would call falling. Okay, you can't ski on that, so that is undefined. Okay, so that pretty much concludes the slope discussion. There's one other thing I want to talk about that they include in this section, which is the idea of parallel and perpendicular lines. Okay, so first of all, let's define this to see what this really means and what we can get out of it. So, parallel lines and perpendicular lines. Okay, there's a graphical way to describe these and an algebraic way of describing them. The graphical way of describing parallel lines are two lines that never cross. That's what parallel lines are. They're just lines that are never going to be crossing each other. Okay? Perpendicular lines are two lines that cross, but specifically at a 90-degree angle. Okay? Any two lines will cross, okay? But specifically, when they're perpendicular, they're going to cross at a 90-degree angle, okay? Or if they don't cross, then they're parallel. But anything else, they're just going to cross any old way, okay? That is the graphical way of describing that, how they're going to look, okay? Now, how can we tell that they are going to look like that without actually graphing them? Parallel lines are two lines with the same slope but different y-intercepts. You have to say they have different y-intercepts because if they have the same slope and the same y-intercept, they're just the same line. Okay, but same slope, different y-intercept. Now, why is that the case? Why do they need to have that? If you have different y-intercepts, but they each have a slope of, let's say, 2. Now remember, 2 would be 2 over 1. So that would be up 2, right 1. Up 2, right 1. Same thing here. Up 2, right 1. Up 2, right 1. Notice these lines are never going to get any closer or any further away from each other. Okay, so you have two different y-intercepts and they have the same rate of change. They're never going to, close the gap. Okay, so that's why that has to be the case for them to be parallel. Okay, now perpendicular lines they are going to have opposite reciprocal slopes. Okay? Another way that you can describe that, and some textbooks describe it this way, they say that the slopes multiply to a -1. I personally don't like that because you don't, not that that's wrong or inaccurate in any way, but then you have to multiply. Don't worry about what their product's going to be. They just will have to be opposite reciprocals of one another. So if one line has a slope of, let's say, 3 over 5, a perpendicular slope would be -5 over 3. Opposite meaning different sign, reciprocal, you flip the fraction. If the first one is -2, the perpendicular slope would be positive 1/2. Because remember, there's a 1 under that. Okay? So that's how you determine if lines are parallel, same slope but different y-intercept. Or if they're perpendicular, they just have to have slopes that are opposite reciprocals of one another. Okay, so let's just do 3 examples of this. Now, that'll be it for this section. So what the question that they're going to ask is are these parallel, perpendicular, or neither? And they're going to give you 2 lines. So let's say we have that. Now, if we want to determine if they're parallel, perpendicular, or neither, remember, the one common thread was there's a comparison of their slopes. If we know their slopes, we'll be able to know what they are. Okay? Now, how do we get the slope out of an equation? Slope-intercept form. Get y by itself. So this first one, I'm going to subtract x and get y equals negative x plus 5. Okay. The next one, solve for y. Subtract 2x. Y is negative 2x plus 5. Now, what's important is the slope here is negative 1. The slope here is negative 2. Now, are they parallel? If they were parallel, those slopes would be the same. They're not. Are they perpendicular? If they were perpendicular, they would be opposite reciprocals. They're both negative. They're not opposite. Forget the reciprocal part. They're not even opposite. So in this case, these two lines are neither. Now, what does that mean? They cross in any old way. Okay, so there's nothing special about how they intersect each other. Let's look at another one. So here's our two equations. We need to first solve for y in both. That'll give us the slope. That'll tell us all the information we need. So first one, I'm going to divide by 5. Y equals 2 over 5x minus 3 over 5. This next one, I'm going to subtract 5x. And then divide by 2. Now there's a lot of fractions there, but don't worry, we're not graphing this. We just want to know the slope here is 2/5. Slope here is negative 5 over 2. Are these parallel? That's not the same, so no. Are they perpendicular? Yes. They are opposites. One's positive, one's negative. And we have 2/5 and 5/2. So in this case, these two lines are perpendicular. Okay? A lot of work is involved with these, a lot of algebra. The actual concept being presented here is very simple. Look at the slopes. That's it. It's just a lot of work in the background that we have to pay attention to when we're working through these. Okay, so take your time, be careful. Okay, let's look at one more. Okay, what's really good about this one? This is already good to go. Okay, so y is by itself, slope is 2. Okay, that one's good to go. How about the other one? I'm going to subtract 4x and then divide by negative 2. Negative 4 divided by negative 2 is positive 2x minus 4. And again, what's the slope there? 2. And there we go. We can see that the slopes are the same, but always take it one extra step. If the slopes are the same, just make sure that those y-intercepts are different. Okay, because if they're the same, then they're the same line, then they're not parallel, they're not perpendicular. Okay, so in this case though, they are different lines with the same slope, so they are parallel. Okay, again, the concept is very, very simple. There's just a lot of algebra in the background. Back in chapter 2, I said, if you don't know how to solve equations, then pretty much everything else is a lost cause. This is what I mean. Parallel perpendicular is a very easy concept, but there's a lot of stuff. If you can't solve that equation, you can't even get to a point where you can show, I know what parallel perpendicular mean. Okay, so as always, work hard. Let me know if you have any questions, and I'll see you next time.